All right, welcome. So in this video, I want to talk a little bit about multi-agent systems. As the name suggests, a multi-agent system is a system that is comprised of agents, of course, multiple agents. And like a normal system, we define systems based on their interacting parts. So the parts in a multi-agent system are the agents that populate the system, and then we usually distinguish the agents from the environment that they exist in. Um, as we discussed in the earlier video on agents, there is sort of a way that we can treat all kinds of different things as agents, even if they're not the same kinds of agents as we are. And this process sometimes is extended to also call the environment in a multi-agent system an agent as well, so that we sometimes might call that the environmental agent, or we sometimes split the environment up into different agents that the environment might be comprised of. With that said, we still probably draw a distinction between the agents that we're focused on and the environment itself. Like most systems, a multi-agent system is going to be defined by its rules of interaction, the rules that govern the interaction between the different components or parts of the system, the agents and its environment. So here, using the game of soccer as an example, a game of soccer is a human-based multi-agent system. It has components, so for instance, there are environmental features like the field that it is played upon, which has lines drawn on it for certain rules of the game. There's also the ball, of course, in the game of soccer, and then there, are the nets or the goals that we're aiming to kick the ball into. And so there are rules governing how those different parts interact, although the one that I've called out here is, while the ball must stay in bounds, if it goes out of bounds, certain rules come into play that cause it to come back into bounds. Another rule might govern how agents interact with their environment. So the game of soccer is sort of defined by the fact that you cannot use your hands on the ball, or a more positive version of that rule is that you're allowed to kick the ball. You're not allowed to grab it unless you're the goaltender. And then, of course, also the third kind of interaction that might exist in this trifecta would be the agent on agent interaction. So a player is not allowed to kick another player, for instance. You're allowed to kick the ball, not another player. So there are rules governing about how players are allowed to interact with one another on the field as well. And of course, these aren't all the rules of soccer, but when we combine all the rules of soccer together, we use them to define the multi-agent system, which is a game of soccer, and we use that to draw judgments about the activities that are carried out. For instance, by using the rules of the game, we can determine who won the game or who lost the game, or if there were penalties in the game, and so on. The rules help us govern and make those specific judgment. And of course, sports are just one kind of multi-agent system in human society. Human society is dominated by all kinds of different multi-agent systems, whether they be cultural rituals, or businesses, or political organizations. There are many kinds of multi-agent systems that we can study just among humans. Of course, the focus of this video series is on artificial agents and artificial systems. So we will stress that when we start thinking about multi-agent systems from an AI perspective, we are usually thinking of it as one that in some way or another comprises some artificial agents. So here we say multi-agent systems can be, all biological agents, all humans, like I just mentioned, or we could have some robots involved in it, or it could be all robots, it could be all artificial agents. Maybe you can imagine some rovers on Mars communicating with each other and trying to, gather data and such without any human interaction. Or, of course, there can be combinations of both. You might have a team of robots that then is being, led or instructed by a human leader, or vice versa. There could, any kind of combination that you can imagine of both human and artificial agents. So speaking of Mars rover, here we have an example of a little rover robot. And one of the things that defines agents within the multi-agent system domain is that they are usually locally present inside the environment. So if you recall from our discussion of agents, one of the properties of agenthood is that it exists in an environment, or we say that more when we want to stress this, we sort of say that they are situated in the environment. They are in a situation, and another way I like to say that is that they have a perspective on the environment. And this is an idea that we call locality, which is that every agent in the system is only going to be able to focus their sensors on a sub part of the system, and as a result they're only going to have a limited or partial information about the overall system and the environment that they exist in, and maybe the other agents that might also exist in that environment. And so because of this limitation, the limitation being that they don't have access to all the information in the system, this causes some need for them, for instance, to maybe want to interact with one another, to maybe communicate what they have learned or seen. So maybe our little Mars rover goes out and explores part of Mars, comes back with some information about what's over there, and wants to share it with the other robots that is part of its team so that they can use that information in their problem solving as well. So again, we call this locality, and it's a feature of multi-agent systems, and it is, even though it can be sort of seen as a drawback that wouldn't it be better if everything had global information, it can be exploited, this locality dynamic, to do some really interesting and powerful things. So another aspect of agenthood that comes over into multi-agent systems is that a part of our definition of agenthood was that agents have some agenda. That is, they have a little bit of autonomy. They have goals and desires possibly, and then they have their own means through which they're able to try and achieve those goals, if they can. And because of this, again, we're gonna take that autonomy and we're gonna bring it into multi-agent systems. That means that within a multi-agent system, there's usually not going to be one agent that's sort of the boss agent or in control of all of the other agents. This does not preclude some kind of organization or structure or hierarchy within a multi-agent system. We could have a team, and there could be a leader of the team, for instance. But in general, we think of multi-agent systems as being systems of agents that control themselves. And then through their interaction, through them choosing their own ways to interact with one another, choosing what to share, choosing what information to share, choosing who to share it with, and so on, that's how the system solves a certain problem. So again, as a bit of an example here, I have maybe some ants. Ants are known, despite having a queen ant, the queen ant doesn't tell all the other ants what to do. She's just mostly in charge of breeding. And each ant sort of follows its own simple little instincts or program that it uses to determine its behavior. But in combination, the whole colony of ants might be able to find a pathway to a food source and then efficiently transfer that food source back to the nest for the queen and for the other ants. And so we call this sort of a decentralization, or this idea of no centralized control means that there's decentralized problem solving going on. And humans are great at decentralized problem solving, although we do also like to centralize some of our control in certain of our human institutions. And ants are the same way. Ants, termites, bees, and so on also have a very social culture, but it's a decentralized social culture, and they've evolved that way, as have we. And the idea that sort of comes along from this then is that any coordination or cooperation that ends up emerging from these decentralized multi-agent systems, we usually call that self-organization. And self-organization doesn't only apply to multi-agent systems. We can have self-organizing physical systems or self-organizing chemical systems. You might still call them chemical agents. That's a common phrase that we would use, but we might not, the chemists involved there aren't necessarily thinking of this from a multi-agent system perspective. They're thinking of it from a chemistry perspective. And so self-organization is, again, a very interesting principle that is studied. That's one of the reasons why ants and termites are very fascinating for us to study in this regard, is because they're able to organize in very elaborate and interesting ways, some ways that are maybe even more elaborate than humans are able to do. One of the key features of multi-agent systems, and it also characterizes the unique nature of ants, is the need to communicate information. As we mentioned earlier, the situatedness, the locality principle, tells us that our agents are only going to have information related to their local area in the environment. Taking that a step further for our ants, but this is also true of a lot of artificial systems, is our ants are not super sophisticated. They don't have a lot of problem-solving skills, and they can only perform some simple behaviors. So they, their need to communicate, they can't speak, for instance, so they can't sit down and have a conversation about, where's the food. If you want to communicate that way, they have to communicate in some other way. Now, of course, ants and the other eusocial insects have evolved very interesting ways of communicating through pheromones for a lot of them, others through other kinds of behaviors. But pheromones are just, simple chemicals that are emitted by the ant. Think of it sort of as a smell, because that's sort of how they interact with them. They can smell the pheromones, and depending on what kind of smell or pheromone has been released, it sends different messages to the ants. And this is just an interesting kind of communication system that allows them to say where food might exist, and then they use that to form little pathways between the mound and the food. So communication is important in multi-agent systems so that you can get some coordinated behavior and coordinated action amongst the agents of the system, whether they're engaged in a cooperative task or a competitive task. So there are different kind of ways that we can communicate. I mentioned speaking to one another. That's commonly how humans do it, through direct communication. And of course, speaking is just sort of the natural way that humans evolved to communicate. We also then developed writing, and now in modern days there are many ways that we can deploy writing or speech through other technological means, texting or writing an email or sending a voicemail or actually calling someone on a Zoom call or something like that. All of these are different ways that we might have direct communication between individuals. Another interesting and cool kind of direct communication that is mostly in science fiction for humans, which is the idea that we might be able to transfer information directly from our brains into our receiver's brain. That might be that in the future, certainly future for me in terms of technology that might help us do that. But within artificial multi-agent systems, this is something that we literally can do. We can literally have one of our agents just send a message from their brain directly into the brain or whatever controller it is that's controlling the other agent. And sometimes that's what we do. That's the kind of messages that we send in a multi-agent system like that, instead of having to send it through some environmental medium like the air. When we speak, we kind of think of it as direct communication. I just move some muscles in my mouth and words come out, and then you hear them in your eardrums and they come in. But there's actually this intermediary medium, which is the air or the space in between. And if you're watching this on the internet, there's also the internet in between us. There's a whole bunch of things that have moved that information from my mouth into your ear. And all of that is just a medium through which we communicated in the environment. So in some sense, when we speak to one another, it's not really direct. What we're actually doing is we are encoding our communication into the environment in some way in the form of sound waves of vibrating air particles. And that encoded message hits a very sophisticated decoder, which is our eardrum, and then the brain, the neural network that's attached to it, that can hear those vibrations and then translate those weird sounds into actual meaning, and that meaning, of course, into other thoughts or other action that we might have. So on the one hand, we might think, okay, speech is a great example of direct communication, but when we get down to the nitty-gritty and we look at it, we realize actually we're communicating through the environment. Another way that we can communicate is called global communication. That's where we might do a broadcast to everyone. Direct communication we usually think of as being one-to-one, so I talk to you, you talk to me, or maybe one to a small number that are in my local area. So if I speak, everyone around me can hear me, but not people that are far away. Global communication, is, at least technologically, is more like a Twitter or a global chat room where you can post some information and everyone can see it. Everyone is brought to its attention. Or maybe more direct would be like an Amber Alert, where every single person who has a phone gets a message sent to their phone at the same time. Those are more global communication And then, as I mentioned earlier, just like we communicate through the environment with our speech, translating our speech into the environment, that's how ants communicate as well. This is the environmental communication avenue where we leave messages in the local environment. Ants sort of leave these little chemical messages where, the little smells that other ants can smell, and the smell says, hey, there's food over here, or oh, this is the way back to the nest, or whatever it might be. And you can imagine humans doing this too. We actually do this a lot. I never met Aristotle, for instance, because he died a long time ago, but he left a little message in The World, which was a book or some writing that he wrote back then. And as a result of 2,000 years of people just bringing that message along with them, I can hear some of the things that Aristotle said from 10,000 years ago, or more 2,000 years ago, not 10,000 years ago. So these environmental communication technology has existed in humans. That's what writing is. Also some of our artwork and so on, other cultural creations. And so humans have been using environmental communication for a very long time, while it's also very common in the animal world, specifically in some of the more social animals like ants and other insects. So because communication is important in multi-agent systems, one of the main things that agents have to communicate in multi-agent systems is about their task that they're trying to perform, and then the resources that they might have to bring to bear on that task. And keeping in mind that some of the resources that you might need to bring to bear are other agent resources, or think of that as human resources, other agents that I might need to make a team to do the task that I have before me. I might not be able to do it just by myself. And so a lot of what goes on in multi-agent system research is research around, well, how can we negotiate how to distribute resources, be they agent resources or just other kinds of resources, and how do we decide which tasks to solve and allocate those tasks to the different agents that might be able to solve them. And so this is a very complicated task, and as you can imagine, there's not going to be one sort of right answer to do that. And because we're also trying to avoid centralized control, remember multi-agent systems are often about decentralization, we like to have more decentralized means of deciding what this might be. So not some hard fast rule, agent A and agent B are always a team and they always share resources. We want something that allows for free flowing of agents to make their own decisions, and then also hopefully achieve together some global optimum, or not necessarily an optimum, but achieve some global goal that we're trying to achieve as a system. So one of the key tools that we use in our negotiations in multi-agent systems are auctions. And auctions exist, of course, in human multi-agent systems as well. But the way that they are typically deployed in multi-agent systems, artificial multi-agent systems, is that if we're auctioning resources, or we might also be bidding for or auctioning tasks, we kind of have two different ways that we go about that, only because those are kind of opposite ends of the spectrum. On the one end, when we're bidding for resources, usually we think of that as that's a typical auction in the human world, where maybe there's something that we want and we want to get it, so we're going to bid on it by offering value to try and get it. Now in an artificial multi-agent system, what we use as our value is we bid relative to our need for the item, or how much we think that item is going to value us in the task that we're trying to perform. So by coming up with some estimation or evaluation of how much its value to my task, and each of us who might be bidding on it comes up with our own personal evaluation of how much this resource is valuable to our task. The goal, or the hope, is that by giving it to the person with the highest bid, that this will lead to hopefully optimizing for everyone, that the person giving it to the one with the most need is probably the one that's going to achieve the most good or the most change in the system relative to that resource. Instead of giving it to someone who doesn't need it very much, who just kind of wants it, that might not make a major change to the overall system. So that's sort of one way how we would bid the resources. Now tasks it's the same, it's just the opposite side, which is task. It's more about the cost to me. How much is the cost? And so instead of thinking of bidding for some resource that I might need, some tool I might need to perform my task, we now start thinking about, maybe delivery, maybe an Uber Eats kind of scenario, where when we're looking at the jobs, the tasks that are available to us, the ones that we might want to perform, we evaluate them based on how much it would cost me to perform that task. So I want to bid the ones that are low cost for me. And so there's this inverse sort of bid structure now, where hopefully we would distribute tasks to the least costly individuals so that overall we're minimizing the cost in the system. So on the one hand, in the first scenario, we're trying to maximize the overall value to all individuals. So that's why we give it to the person we think that values it the most. And then in the second scenario, we want to minimize the cost of the tasks that we're performing. So that's why we might distribute tasks to the people that it would cost the least to do that. And so these are just common ways. And of course, this is a whole field of study, so there are many nuances to those different kind of auction strategies, how you would set up the auction, how you adjudicate the auction, and so on. But auctions are a very popular way for negotiating the distribution of resources and tasks. The other thing that tends to come out of this type of negotiation, and it's sometimes necessary for the types of tasks that we're performing, is the idea of forming teams or coalitions. And so it can be a case where maybe if every individual is trying to achieve their specific individual task, and through the bidding we can get to some kind of deadlock, where no one's willing to give up the resources that they have because they need them to perform their task. And this can lead to sort of an overall failure of the whole system to achieve any value in the worst case, but at least, not reaching towards optimum value in some of the better cases. So as a result of this, sometimes what we want to do is have mechanisms or means for our agents to form into teams, again, naturally, emergently, self-organizingly, because we don't want, again, there to be a central dictator saying, you guys team up, you should form a team, and so on. Instead, what we like to do is use some of the auctioning framework that we had before to have different agents that have different or have similar tasks that might want to team up together on the same task. So maybe in some scenarios, if we're bidding on tasks, if more than one agent has bid for the same task, it might be valuable to assign more than one agent to that task if that task can be efficiently carried out by more than one agent. Likewise, with resources, sometimes coalition forming is a way that trading or pooling of resources might be successful. Neither, agent A or agent B might have the resources needed to perform their individual tasks, but if they pooled their resources, maybe both of them would have the resources needed to perform their individual tasks, or maybe performing their tasks together somehow lessens the resource costs of those tasks. And those kind of coalition forming or coalitions should be formed for the advantages that they bring to the overall system. So again, another large area of multi-agent system research is dedicated to how can coalitions be naturally formed and then dissolved when they are no longer needed, so that new ones can be formed, of course, and what kind of structures would we need to have fluid evolution of coalitions over time. So one of the applications of multi-agent systems that we have seen in recent years is the swarms of drones that are, in some places replacing fireworks. And this is an example, I think, from the Beijing Olympics, where a lot of drones were made into this dragon shape. And again, the coordination needed to have, this looks like hundreds of drones fly in formation. And it's one thing on a computer simulation to have a bunch of pixels move in formation. That's kind of easy to do. But when you're flying drones, it's not quite as easy. They're actually flying against the wind and so on, and they need to communicate with one another their current location so that they can coordinate. And so there's a lot of really sophisticated technology involved with trying to get these types of multi-agent systems, again, we typically call these now swarms, to do the behaviors and perform the way that we want them to perform. Another application of multi-agent systems and this type of automation right now is fleets of self-driving cars. Of course, there's still challenges involved with getting our self-driving cars up to a level where we can be comfortable and confident with their ability on the road, of course, for our safety. But assuming we can get them to that level, and something that might help us get them to that level is having them coordinate with one another in a multi-agent system, so that the whole system is coordinated to maximize, for instance, traffic flow, and make sure that everyone is able to get to where they're going in a reasonable amount of time. So this is, again, still an open question in multi-agent system research. I mentioned it is a multi-agent system research, but this is definitely in the intersection of so many different areas of AI research, and not just AI research, public policy and whatnot as well, public safety. So there are lots of different areas that are involved to try and make this happen, of course, multi-agent systems being just one of them. All right, that's all I really wanted to say in my introduction on multi-agent systems. So hopefully you've got an idea of how multi-agent systems are applied and have an impact in artificial intelligence today. And thanks a lot for watching, and we'll see you again in that next video.